Welcome to this session. This is the final installment on balancing equations with stoichiometry, one of the tools of the trade that you'll use the most. My name is Renee McCormick. I'm the National Director of Science Programs for the National Math and Science Initiative, and I'm really glad you're here. Arguably, stoichiometry, like I said, is the skill that you're going to use the most throughout the year. So the faster you embrace it and make peace with it, let's just say the better your grades are going to be, because this is not going away. It's not going away all year. So getting good at it early and being able to demonstrate that often is only going to make you a happier camper, as well as all the grown-ups in your life. So let's talk a little bit about balancing equations. I'm always working under the assumption you had a first year course and that you've done some of this before. Hopefully you've done a lot of this before, and that this will be review for you rather than a clean teach. But you can always fast forward me, and you can always repeat what you need to repeat, and I'll never be the wiser. So chemical reactions are a result of a chemical change. Where atoms are reorganized into one or more new arrangements, bonds are broken, which requires energy. It takes energy to break a bond. When new ones are formed, energy is released. So a chemical reaction transforms elements and compounds into new substances. But we have to obey the law of conservation of mass, and so a balanced chemical equation shows us the relative amount of reactants on the left and products on the right, by molecule or by mole or by liter of gas if it's gases at STP, standard temperature and pressure, etc. So then there are some subtle details which you may have happily ignored throughout your life thus far, but you can no longer do that. And so this little S, L, G, and AQ stand for solid, liquid, gas, and aqueous solution, meaning it's not a pure substance, thus it's not just a liquid. Don't misuse that word. A liquid in chemistry is a pure substance. Bromine, for instance, can be a liquid at room temperature. So aqueous means something is dissolved in something else, and there are many solvents in the world. Water is just the one that's probably your favorite. So we call these the state symbols, and again, they correspond to solid, liquid, gas, and aqueous solution. No energy or time is alluded to when you look at a balanced chemical equation. There's lots of room for us to study those sorts of things later on in the course. We're at the beginning of the course at this point, so we're just trying to get down some basics. So Antoine Lavoisier, and yes, this is a Texas twang. No, it's not going away. I may have just butchered that, but that's how I learned to say it. He's the gentleman that came up with the law of conservation of matter. So this is all his fault. It states that matter can neither be created nor destroyed, so that's why you have to balance equations. You have to have an accounting system, since matter cannot just poof, disappear, or double poof, appear out of nowhere. So to balance the chemical equations, we have some little steps to follow. We're going to begin with the most complicated looking thing. That's often the scariest looking thing. That's the best place to start. If you can get that to work out, then you may be finished by the time you get that one just settled with everything else that's in the equation. If that doesn't work, then double the scary looking thing. So we're going to save anything that's elemental for last, like O2, H2, anything that's just a pure element. And then if you get stuck, like I just said, double the most complicated looking thing and try again. This is why you do this in pencil, so you can erase. So you do need to know that metals and halogens are going to make an MX compound, so that anytime a metal and a halogen react, you're just going to make that salt. You're familiar with this. Sodium metal plus chlorine gas makes NaCl, and to balance it, we would need two of these, because we must have two of these, thanks to that little 2 right there. I need to put that 2 in, which forces me to put that 2 in. Now, there's a million hydrocarbons in the world, literally a million, not an exaggeration this time, and or oxygen atom plus O2 type arrangements. Anything that adds a hydrocarbon and an oxygen together, you're probably going to end up with carbon dioxide and water as the products, especially if something is burned. But for the love of God, realize you're going to make the oxide of what you burn. We burn things other than actual hydrocarbons. So I've actually seen kids on the AP exam say have to write an equation for the statement magnesium ribbon burns in air. Magnesium ribbon is just a ribbon of solid magnesium. And they actually write this. Don't be this person, I'm begging you. That is just nonsense. So what it really would form is a magnesium oxide, which is MgO, which would force me to put a 2 here and a 2 here. How do I know it's MgO? I'm looking at the periodic table. I know that the two A's right here are plus 2 metals. So if I'm going to put oxygen with that, oxygen is a -2. It's over here in the -2 column. That's going to make me have to make MgO plus 2 minus 2. So that balances out as a little chemical formula over here on the right-hand side. And then elemental oxygen is a gen. Hydrogen, oxygen, nitrogen, and all the halogens come as diatomic molecules, 2 of them in a molecule. And that forces me to have to put a 2 here as well as put a 2 there. All right, so also know that any time that you form H2CO3, lovingly known as carbonic acid, you've had a soda in your life at some point, and those little bubbles that come out, those are carbon dioxide bubbles. And then when you say it has gone flat, that means that all the carbon dioxide has bubbled out, it's no longer fizzy anymore, and that the reason it tastes kind of odd is that it has made a lot more water than what was originally in the beverage. So never write carbonic acid as a product because, again, it's going to spontaneously decompose in an open container like a beaker, a flask, a test tube. Now, if you've got it sealed up, that's what we do, is we bubble carbon dioxide into a sugary water solution to give it that fizz when we make soda pop. But you know what happens if you leave the lid off. And then metal carbonates are going to make metal oxides and carbon dioxide. So this is just a few general sort of things that you might as well give up and memorize out of self-defense, because you're going to see them quite a bit through the course, and you don't want to constantly be scratching your head wondering how that works. So these are just this little chart is just some good information that's conveyed by balancing chemical reactions, and this one is conveyed by the balanced equation for the combustion of methane. So methane is CH4, and there's a whole naming lesson on the hydrocarbons, but essentially they're normal after you get to like 5 carbons, and you talk about pentane, because you know that a pentagon has 5 sides, so this pentane has 5. It's the first ones that give you trouble: meth, eth, prop, and bute. I'm not proud of this, but when I was trying to learn this myself in college, me eat peanut butter is what I came up with to be able to remember those, because those prefixes had nothing to do with geometry. But after you get 1 carbon, 2 carbon, 3 carbons, 4, then it gets normal: pent, hex, hept, oct, etc. So along the way, you need to probably review. It would take you maybe half an hour to get the naming down of hydrocarbons. Not to worry about it right now. This is just basically showing you the accounting of what's going on. And we can account by molecules, we can account by moles, and again, if it's gases, we can account by liters at STP, but we can also account by mass, which is accounting by grams. Any one of these things are pieces to the puzzle called stoichiometry. And I love the name stoichiometry. It's one of the most fun things ever. I've even heard Sheldon on the Big Bang Theory confess that he likes the name stoichiometry as well. All right, so chromium compounds exhibit a variety of bright colors. Very nice to know, because that's what fireworks and such things are all about. And when solid ammonium dichromate, which is NH42Cr2O7, a vivid orange compound, is ignited, then a spectacular reaction occurs. Love spectacular reactions. So although the reaction is actually somewhat more complex, let's just assume here the products are solid. Products, they're telling me something I need to know. Products are solid chromium 3 oxide. You know that Roman numeral 3 is your friend. I don't care how many times you see it written wrong on the web and in other sources. That parentheses needs to snuggle right on up to the metal, because it's telling you, hey, that's a +3 metal, and you don't have to think about it. And then nitrogen gas, which you know is a gen, so it's diatomic, and water vapor. So they gave this all to me in words because they're mean. So they want me to balance the equation for this reaction. So let's start with the ammonium dichromate. There, they gave me that formula to get me started. So off to the races. I know the answers are down there. Don't look at them yet. NH4 twice, Cr2O7. We'll spare you memorizing that Cr2O7 is called dichromate and that it has a -2 charge, but we won't spare you that ammonium is NH4, because it's ammonia with an H plus riding piggyback on it, and that plus is from that H plus charge. So that's why I need 2 of them, because the dichromate is a -2. So they tell me that is decomposing into chromium 3 oxide. So you start off with chromium and oxygen and you ask yourself some questions. You know that oxygen carries a -2 charge, and they've told you that the chromium is a +3. That's the Roman numeral moment. And so I need 2 of the 3's and 3 of the 2's. In my class, we called that a 2-3 trick. You need 2 of the 3's and 3's of the 2's. So it's Cr2O3. That way both end up being a +6 and a -6, and that makes a neutral formula. And then nitrogen, so I need that too. And then my good buddy, water. So the scariest looking thing by far, I suspect we would agree, is the species right here. And so what's that going to do? Well, I've got 2 nitrogens on each side already. I'm going to save those hydrogens because that's 8 hydrogens right there. Think about that for a minute. I've got 2 CRs, not a problem, but I have 7 O's. So if I put a 4 right here, that'll take care of my 8 H's. And now let's see what that does for my O's. Did that work everything out? So I have 4 O's there and 3 O's there. That means I have 4 O's right here. So that's a total of 7. Hey, that worked. Okay, and then I've got 2 CRs, no problem. 8 H's, that's 8 H's as well. And 2 N's, and that's 2 N's. And we will call that a day. So that is our balanced equation. So start with a scary looking thing and work your way through there. And if you get stuck and you hit a prime number and something just won't work out right, then double the scary looking thing. So how about exercise 14? At 1,000 degrees Celsius, I don't want to be anywhere near that, that's very hot. Ammonia gas, NH3, reacts with oxygen gas, we know that to be O2, to form gaseous nitric oxide. Thank goodness they gave me the formula. It's just NO, and water vapor, and we know that that's H2O. So the reaction is the first step in the commercial production of nitric acid by the Ostwald process, in honor of, guess who? Go ahead, guess. Yes, Ostwald. Not to be confused with Harvey Oswald that assassinated President Kennedy. Okay, there's a T in there. Now, balance the equation for this reaction. Okay, here we go again. Ammonia. Ammonia is one of our favorite things to discuss because this idea of making ammonia is pretty much what cured famine across most of the globe, because it's one of the first steps in making fertilizer so that we could grow plants for food in places that were inhospitable to plant life by nature. All right, so my ammonia gas reacts with oxygen to form nitric oxide, which they told me, and water. That's not very pretty. That's much better. All right, so what do you figure? What are we going to do? I'm going to go back to red. We got a lot of scary looking things here. Let's go with the ammonia and kind of work from it. What do you figure? We got an N on each side. That's not very helpful. I got 3 H's on the left. I got 2 on the right. So that could be a 2-3 trick going on here. So let's try it. So if we put 2 here and we put 3 here. Now I've got 6 H's and I got 6 H's, but I got 3 O's and another O makes 4. So if I put a 2 there, does that work out? No. Why not? Because I got to put a 2 here. So that's trouble, because now that's got everything goofed up. So let's figure out what we should do from there. Let's try again. I'm letting you think. All right, so when we tried this, a 2 here, and that would force a 2 here, what did we get? I'm going to save this elemental thing for last. I've got 6 H's, so if I put a 3 there, we tried this before, I've got 6 H's. Now what are my total O's? I've got 3 O's, and I've got 2 O's, and I've got 2 O's over here. So that is 5 O's. Agreed? That's not 50, that's 5 O's. And so what to do? Well, if I get rid of all of this mess and start again, I'm thinking I need to go for a 5 on that oxygen. And there are many ways to think this through, but this is what's coming to my brain. I need a 5 there, because if I get a prime number in here, then often that makes everything else work out. So let's start with that. So I have 5 O2s. I got 2 sources for oxygen, but what we do know is that I've got to have a way for them to add up to 10. And so if I put a 4 here, let's see what that does. I tried a 2 earlier and that didn't work, so I'm going to try 4. I'm trying doubling it. So now what have I got? I got 4 n's. So that would force a 4 here. So that would give me 4 O's of my 10 that I need to spend. So that leaves me with 6 O's if I put a 3 there. Does that help? 4 n's. 4 n's. Check on the n's. Check. Okay, H's. 4 times 3 is 12. And 3 times 2 is 6. So that's not going to work. Alright, so 4 times 3 is 12. That would force me to put a 6 there to get 12. Alright, so now I've got the H's. Check. Alright, O's, those troublesome O's. I have 10. So I have 4 here, and I have 6 here. And yippee skippy, I got it. One more time from the top. Normally, I would have put a 2 in front of the ammonia, and most of the time, that'll work out. When it doesn't work out, come back and double the scary looking thing, because ammonia to me is much scarier than anything else on here. And so when 2 didn't work out with the doubling, I doubled the double. So that made 4. And ultimately, I know I'm headed somewhere if I've got a prime number in here, because that means I can't reduce it any lower. And so just make yourself a little checklist and work it out from there. You're not going to see something this complex, most likely, on the AP exam, but you are going to see it in your homeworks, because we want your homework to be harder than the AP exam, so that when you get to the AP exam, you're like, piece of cake, I got this. Alright, so now some stoichiometric calculations. It's just such a fun word. So stoichiometry is defined as the study of quantities of materials consumed and produced in chemical reactions. Stoichiometry, like I said earlier, is the most important thing that you're going to learn as you embark upon AP Chemistry. Get good at it, and you'll do well all year, because this never goes away. You're going to use it all year long. If you're going to be stubborn about it, then you're going to lose points all year long. Make friends with it. I don't do stoichiometry the way other people do it. I don't do it the way most books do it. I'm about to show you an alternate method. I am not trying to fix you if you are not broken. If you had a first year course and you like stoichiometry because you're good at it, then go for it. Ignore everything that I'm about to do and just stop me now, work through the rest of the problems in this handout, and then come back and check your answers with me. But I'm going to show those that would like to know a different way. And there's a method to my madness. I know, but you may not know, that you're going to be doing equilibrium as one of the hardest topics in this course. But you're not going to get there till later in the year. January at the earliest. Hopefully your teacher doesn't wait till right before the AP exam to get to that, because that's scary. But the way I'm going to teach you to think doing stoichiometry now in a little table method is the way you're going to have to think when you get to equilibrium, and you're going to thank me when you get there. Again, I say, you can just go to have a good old time with dimensional analysis and just work your way all the way across the page working all of this stuff out. It's just not going to be how I do it. So apologies, I'm not trying to confuse you. Again, if you're really good at dimensional analysis, you may not even want to listen to me for this. You may just want to skip on past. Alright, so no matter which method you choose, you have to be good at the following skills. So you have to be able to write correct formulas. That requires knowledge of some polyatomic ions and being able to use the periodic table to deduce what you have not had to memorize. Let's take a moment. That means that all of these guys here traditionally make +1s. These make +2s as their oxidation states. Starting at the opposite end over here, these are the noble gases. They used to be the inert gases until a jerk came along and made a compound called xenon tetrafluoride. Incredibly reactive, that fluorine. Xenon tetrafluoride, and then they weren't inert anymore because someone had made a compound from it. I actually ended up having that professor later in life when I went back to school myself. Alright, so these are the halogens, and they are all -1. These are typically -2, and we don't get into these much, but these two we use a lot. These can be all sorts of different things, plus or -3. So just knowing a little bit about the anatomy of the periodic table can go a long way to help you with writing correct formulas. Then you also must be able to calculate correct molar masses. You may call them formula weight, you may call them molecular weight. I do not know why the grown-ups in your life cannot get along, but you'll hear me say that throughout the year. But molar mass, or formula weight, whatever you call it, you got to take a formula like H2O and you got to go, each hydrogen is worth 1.01 and there are two of them. So that's 2.02. I can do that math in my head. Oxygen weighs 16.00. So the molar mass is equal to 18.02. Now, you don't need to memorize molar masses. You don't need to memorize atomic masses. But at some point, you use them so often, you kind of end up remembering them out of self-defense. All right, then you've got to be able to balance the chemical equation, and you've got to be able to figure out the number of moles any way you wish. I'm going to show you a mole map. That's how I taught my first year folk I normally call the Chem 1 babies. It is not a derogatory term. I absolutely loved them. They were precious. So my little Chem 1 babies, when they were learning things, they learned this mole map. Now you may know already 3 ways to get to moles. I am begging AP chemistry teachers and chemistry teachers of all sorts all across the country to teach all 4 ways. Why teach 3 and leave one out? Because then children don't trust you. Why did you hold that one back? So all of this is about getting the number of moles, which is in the center of this little organizer for you. When you move away from the number of moles, you will multiply in the direction of the arrow. So you multiply to get out to mass from moles, you multiply to get out to number of particles from moles, and you multiply to get to volume. But note that you're going against the arrow if you want to get to concentration of a solution in moles per liter, also lovingly known as molarity, which a capital M as a unit, or the quantity, 2.0 molar solution, could be encased in these square brackets to also mean molarity, mole per liter, or mole liter minus 1. Let the parade of synonyms and like expressions begin. So, if I know the mass in grams, I will go against the arrow and divide by molar mass to get to moles. If I know the gas volume in liters at STP, standard temperature and pressure, 0 degrees Celsius, 1 atmosphere of pressure, 60 millimeters of mercury, 101.3 kilopascals, choose your pressure unit. And then standard temperature, again I said 0 degrees Celsius, but that could also be reported as 273 Kelvin. So at STP, standard temperature and pressure. If I've got the amount of gas in liters, then I simply divide going against the arrow by 22.4. If I have the number of particles to get me started, you recognize that as your good buddy Avogadro's number. Going against the arrow, and thus I would divide. Go the other direction, and you multiply. So, concentration of solutions in moles per liter. I would go in the direction of the arrow to get to number of moles and simply multiply the molarity times the volume in liters. Just make sure your unit is liters, not milliliters. Oh, but wait, what if it is milliliters? I can do molarity times volume in milliliters and come out with, you guessed it, millimoles. We will be using that throughout the year. So I wish you'd learned that in first year, and if you had a really, really good teacher, then you did. If not, then hey, you have a really good teacher now in class in your AP Chem class, so embrace this way to do it as well. It being calculate the number of moles. Okay, so now here's what I do. And again, you don't have to do it this way. If you're good with this, you can just end this recording right now and just check your answers. But if you're struggling or you're learning this for the first time, give it a shot. So this is a template. It's the pattern as best I can give you. You're going to create a chart. So here's a typical example. Calculate the mass of oxygen that will react completely with 96.1 grams of propane. Okay, I got to know what propane is, or I've got to look it up. Me eat peanut butter. That's the P is third, so that's C3, double it, and add 2 for the ane ending. So that's 3 times 2 is 6 plus 2 makes 8, so C3H8 is the formula for propane. So C3H8 is going to be reacting with oxygen because that's what burns or combusts or anything that implies synonyms to that means. And so I've got to make carbon dioxide and water. So balance the equation. I start here with that C3, going out on a limb and put a 3 there. I see 8 here. I'm going to go out on a limb and put a 4 there, and God willing, save that element for last and we can make this work out. So that I have 6 O's and 4 O's, which is be 10 O's. They come in pairs, so put a 5 right there, and we have a mole-to-mole reaction. So then, and by the way, you need to put this here until you're used to it, but at some point you can drop down all these headings right here, but you're going to see it for a while until you get kind of used to it. So then I put the molar mass above everything. Resist the urge. I'm begging you, resist the urge to multiply the molar mass by anything. It's simply the 3 carbons plus 8 hydrogens. The fact that there's a 5 here does not quintuple the fact that oxygen's molar mass is 32. It's still O2, twice times 16 for a mole of it. We just happen to have 5 moles of it. So get all the molar masses up above, put the mole to mole ratio. I'm just bringing down the understood 1 in front of propane, the 5 in front of oxygen, the 3 in front of carbon dioxide, and the 4 in front of water. Just helps you focus. Then the next thing we're going to attack is number of moles. Calculate the number of moles of something, anything, to get started in a stoichiometry problem. And then there's going to be an amount. Is this stuff coming at me in liters? Is it coming at me in grams? Is it coming at me in molecules? There's going to be some amount, some unit of amount that's going to ultimately go with it as well. So this is just telling you what to do here. And now we read the problem and put in an amount. In this case, it was 96.1 grams of propane. So we write 96.1 grams of propane, and we are off to the races. First thing to do is, again, find the number of moles of anything at all. Something, anything. So 96.1 divided by its molar mass, which is conveniently sitting up on top, gives you a screen full of numbers of which you will round. Well, how do you know how much to round? Look at what the amount was. The amount was in 3 sig figs. Stick with 3 sig figs. Don't write down the calculator vomit that you currently see on my screen. Just round the 2.17 to 2.18. And using a graphing calculator is going to speed you along. If you've not made peace with your graphing calculator, yeah, there's a screencast for that. Quiet place, favorite beverage. Do it over and over again until you become one with the calculator. Because you're going to be able to go a lot faster than the other kids in the country that are using ordinary calculators. You're also going to make fewer mistakes. But you do need to be on the latest operating system. So if you'll go second plus on your graphing calculator, and I'm using an 84, okay, you may be using an 83, but you need to see what the latest operating system is. If you're on an 84, then it's 2.55. Find your favorite calculator geek to help you upgrade that operating system. I think I may talk about it in the graphing calculator tutorial, but I'm not 100% sure. Or you can always use that new thing called the internet, and I'm a fan of Google, but you might prefer Yahoo. But you could say, upgrading my TI-84 Plus calculator, and it will tell you how to do that. So I'm going to quit that screen. Left my number intact. That makes me happy. And so I've got my 96.1 grams, and now I can find out the grams of everything else. Again, how did I get the 96.1? I simply used the mole map. I started with the 96.1 grams, divide by the molar mass because I'm going against the arrow, and get the number of moles. Now I use this molar mass to find the moles of everything. If 1 equals 2.18, then oxygen is 5 times that because it's got a 5 sitting right there versus this 1. I'm just using a simple ratio. So that's 10.9. 3 times 2.18, 6.53. 4 times 2.18, 8.71. Write them all down. You never know what you're going to need. So it takes you seconds to get all of them. By now, though, you forgot what they're asking you. So reread the problem, and to determine which amount was asked for, so here's the payoff. AP problems are going to ask for a bunch of different things, so this method may seem like it takes longer if you're looking for a single thing when you're doing homework, but I need you to have just a tad of faith in me that my students did really well on the AP exam, and I want you to do really well on it. And being able to do this, you'll be so much faster than everybody else who's cranking out all that dimensional analysis through a 5-step AP problem. So what do they really want? They want first for us to find the mass of oxygen required. Well, go to oxygen and see that it is 10.9 moles. So I need 10.9 times its molar mass, and its molar mass is 32. Twice times 16 is 32. I don't need a calculator for that. So I get 348.8 as my answer, but we'll round it to 3 sig figs and call it a lovely 349. So 349 grams of oxygen at this point. So humor me. What if part B turns around and asks you for something, whoa, totally different? Sorry, don't mean to make you dizzy here. It asks, what if it asks for liters of carbon dioxide at STP? No problem. I still use the mole map, or what you have memorized is how to deal with moles. I start in the middle of the mole map with 653 moles, and I'm multiplying in the direction of the arrow times what it says, which is 22.4. So again, let's lock onto this 653, and we're being asked for liters at STP. So I'm going to make you dizzy. So what do I know? I know volume in liters, and I'm going against the arrow, so I will divide by, that doesn't look like divide by, does it? That looks like divide by 22.4, and I will arrive at moles. Then I can multiply by 6.02 times 10 to the 23rd and tell you particles. I can multiply by molar mass and tell you grams, or I can divide by liters of solution and tell you molarity if you wanted that. So I've got my 653 mole, or 6.53 moles, and I'm going to multiply that by 22.4 liters. So my 6.53 times, so I hit divided by instead, times 22.4 is 146.272. 3 sig figs leaves me with 146. And then what if I want to know water molecules? Well, I can take my 6.53 and I can also multiply that by 6.02 because I know they wanted water molecules they wanted molecules of water. I have 8.71 and I can multiply that by Avogadro's number. I'm going to take a pause for just a second and show you something kind of cool. And you already probably know this. I don't think I'm the only geek on the planet. But you know, you're going to get really tired of typing 6.02 second EE23. You can store that sucker. That's what this button right here is for, this STO button. Store it as alpha, and A is directly under it. See how they're color-coded? So there's my alpha key, and there's my A right there. So store it as A, and it comes back at 6.02 times 10 to the 23. So that way you don't have to type it all the time. Just keep it stored. If you change batteries, it's going to wipe it out, and you'll have to restore it. Just word of caution. Don't want you to goof up on a test. So I'm sitting here with the water at 8.71 moles. So 8.71 times alpha A is 5.24 times 10 to the 24th to 3 sig figs. So my calculator confirms that. And so that's the system. That's how you do it. So it's a combination of mole map and this table. You do not have to do it this way. If you are lickety-split fast at dimensional analysis and enjoy using all of that writing, then go for it. I'm not trying to change you. I'm just trying to help you see alternate methods. There's no one better way than the other. What's better is what works for you. All right, so having said that, it's time to pause me. It's time to pause me and use your favorite method and work through this problem. I'm going to clear my screen. I'll wait on you. Go ahead, pause me. No cheating. Work this out. Welcome back. All right, so let's dissect this little sucker and see how you did. Solid lithium hydroxide is a good place to start. So bad aim, I wanted the black. LiOH. I know hydroxide's a -1 polyatomic ion, lithium's an alkali metal, so it's a +1. So LiOH plus is used in space vehicles to remove exhaled carbon dioxide. You know that to be CO2 from the living environment by forming solid lithium carbonate. Mean when it's in words, huh? You have to know that Li is lithium. You have to look at the periodic table and see that it's right there. So it has a +1 charge. And then that carbonate is CO3. It has a 2- charge. You have to just give up and memorize a few things. So I would need 2 of those to make that a balanced formula unit. And then we can deal with water. All right, so we need to balance this sucker. What do you figure? This is troublesome. So let's try this. Did that do it? I got 2 lithiums on both sides. Yes, indeed. I have 2 oxygens there, 2 more over here for a total of 4. So I have 3 on that carbonate, 1 on that water for a total of 4. This is looking good. H's, I have 2. So I have 2 in water. I have one carbon, and we've already accounted for all of those oxygens. So life is good. So this is a 2 to 1 to 1 to 1 mole to mole ratio. All right, now what? Number of moles would be useful. Find the moles of something, anything. That's how you get started. You know, you've had that feeling before, whether it was in math class or some other science class, of I don't even know where to start. I don't know how to start. Well, you start by writing a balanced equation. Then you start by finding the moles of something. They've got to give you something to get started. And indeed they did. They gave me a kilogram, lovingly known as 1,000 grams. So I have an amount of 1,000 grams. I always change it to grams because that's what molar masses are about. Oh, speaking of molar masses, let's do those. What's the molar mass of lithium hydroxide? Lithium is 6.94, plus the fact that oxygen is 16 even, plus hydrogen is 1.01, and you can probably do that in your head, and I get 23.95. I know that CO2 is 12.01 plus 32. Do it in the calculator if you have to, but there's nothing wrong with your brain. It's a pretty good brain or you wouldn't be here. You wouldn't be listening to me. So that's 44.01. I can't do lithium carbonate in my head, so let's look at this again. All right, so 2 times 6.94 plus 12.01 gives me that much, plus each of those oxygens is 16, and 3 times 16 is 48, and I get 73.89. All right, then what's next? 18.02 for water. You do enough of them with water and carbon dioxide, you give up and you memorize some of them out of self-defense because you just get tired of it. Okay, so now what do I need to figure out? I've forgotten what they've asked me. What mass of gaseous carbon dioxide? So that's what I'm looking for. So I have a 2 to 1 ratio. So if I find the number of moles of lithium and I divide it in half, that's how many moles of carbon dioxide I need. So I take the 1,000 grams and I divide it by the 23.95, which is conveniently sitting up there at the top as its molar mass, and I get 41.75, we'll call it. And that's what 2 is, so divide that in half and I'll find out what 1 is. 2, if 2 is this, what would 1 equal? It would equal half as much. 20 point, what do you figure? Let's call it 9. I'm leaving it in my calculator, but I'm going to have to write something down to show my work. So 20.9. All right, so then how do I answer the question? They wanted to know what mass, so I need grams. So number of moles times molar mass will make that happen. So I'm taking that number that's in the calculator and now multiplying it by the 44.01 for a molar mass, and I get 918.7989 blah blah blah. Do not write all that calculator vomit down. How many sig figs are we looking for? Well, what did they give us? They gave us one digit to work with. Get in the habit of writing how many sig figs outside the problem so you don't have to think about it when you're all finished. So round that gunk on the calculator to 3 sig figs. 9, 1, think about it, 9. And don't leave it naked. What is that? That's grams. That is the answer, all nice and pretty, that they want. All right, so they rounded to 2. Why'd they round to 2? That's wrong. It should be 9 point. Oh, they probably rounded each step, and that's what we don't do on the AP exam. So that's okay. And by the way, a word about sig figs. No vomit. They will give or take one place and give or take one value. So if the answer key says 920 and you write 919, you're good. If you write 921, you're good. If you write 920.6, you're good. They'll give you a spot in the place of sig figs, and they'll give you a spot in the digit of sig figs as well. It's really somewhat generous. Just don't write down a bunch of vomit. All right, shall we try another? Exercise 16, baking soda. Sodium bicarbonate is often used as an antacid. That's what my grandma always taught me to do if I had an upset stomach, is just put a teaspoon of that in a glass of water and drink it. Much cheaper than all that stuff they sell. It neutralizes excess hydrochloric acid secreted by the stomach, and so they gave us a balanced equation, which is very, very kind. And milk of magnesia which is an aqueous suspension of magnesium hydroxide, is also used as an antacid. Which is the more effective antacid per gram? Justify your answer. Well, when in doubt, go to moles. Find the moles of somebody. And if we do that, we can think about the molar mass here in this case. So let's just dive in. NaHCO3 has a molar mass of, pause me and calculate it. I'm waiting. 84.01 grams per mole. All right, and then how about the other one? Mg, and they gave me the formula kindly, OH2. So they gave me that formula, They're not testing to see if I know the formula. Has a molar mass of, go ahead. I'm waiting. 58.32 grams per mole. Now don't get married to those numbers because you got to think a little harder than that. What's the point? This is an antacid. It's going to neutralize acid. So what we're saying here is that 84.01 grams is required for 1 mole of hydrochloric acid, whereas with the magnesium hydroxide, 58.32 is enough to neutralize 2 moles of the HCl. So even without fancy math, you know that this one is more effective. But why? It's more effective since only 58.32 divided by 2, it's 29-ish, only 29.2 grams of MgOH2 is required to neutralize 1 mole of HCl, while 84.1 grams of MgOH2 is required. Oh, the other one, sorry, of sodium bicarbonate, NaHCO3, is required. Okay, so that's what's the scoop there. You have to write a sentence. This is very typical on an AP problem. All right, so new skill coming at you. If you need to pause and go get a beverage, maybe get some caffeine, get a snack, whatever you need to do, this is a good time. Pause me if you need to. I'm going to move on. This is a huge concept. This is a concept that gives most kids a lot of trouble. But it's not difficult. It's a concept you already know in your everyday life. What I need to do is chunk it next to something you can already relate to. Well, I chose hot dogs. You ever notice how hot dogs are sold in a package of 10 while the buns are sold in a package of 8? I've never understood this. I don't know why these companies can't talk and go, hey, you know what? We're going to package 10. Maybe you should put 10 buns in. That way people buy 1 of each. Otherwise you waste 2 weenies. So there needs to be a hot dog summit at some point. But the limiting reactant that limits the hot dog production is the 8 buns. So that is our limiting reactant. That's all it means. So if you've ever, well, here's a case in point. My husband loves chocolate chip cookies. So we buy a bag of Nestle's chocolate chips. We bring it home. Well, he loves cookies. I love chocolate. So I have some tendency to open the bag and sneak a few out. And sometimes I sneak a few out on a lot of occasions. And if I snuck out a half a bag worth, then those cookies are not going to be good. So what would you do? Of course, you would cut all the other ingredients in half and you would make half as many cookies. They would still be of the same quality with the same chocolate chip to dough ratio, but you would cut the recipe in half. That's all this is about. If you get in the kitchen and you cut a recipe in half or you make twice as much, you understand this idea. If you've ever tried to do it and had a limiting ingredient in the recipe that dictates how much you need to cut everything else by to still make a quality product, you understand this concept. All right, so We're going to do this through a very famous process you might as well get used to, which is called the Haber process. Some people say Haber, but it's a German word, so I think, having had 3 semesters of German in college, one would say that as Haber. But I do have a Texas accent, so I could mess that up too. So this reaction is essentially making ammonia for fertilizer production from the nitrogen in the air that reacts with hydrogen gas. The hydrogen gas is obtained from the reaction of methane with water vapor. So this process has made fertilizer very, very cheap, very, very commonly available, and has saved millions from starvation in more developed countries. So this particular exercise is one that the new AP course, new as of 2014's exam, embracing something we call particulate view. So you're going to have to get good at looking at these little drawings and figuring out the chemistry that goes along with them. For those of you that love math and are going to probably have calculus prior to graduating high school, this may annoy you. For those that are not, you may actually enjoy this. So we have 2 situations. It asks us to examine the particle views and explain the differences between the 2 situations pictured below with regard to what is or is not reacting and total yield of ammonia. So 2 items, is or is not reacting and total yield. The little words are what will get you in word problems. Prepositions are important too. All right, so examine situation 1. Here's your hydrogen, here's your nitrogen, and here are your adorable little ammonias that form. Now, from the balanced equation, we know we need 1 of these, 3 of these to make 2 of those. So they've take the little dotted lines and they've packaged them. You need 3 hydrogens for each nitrogen, and since hydrogen and nitrogen are gens, they're all diatomic. So that makes a perfect little package of each one of these makes 2. So 2, 4, 6, 8, 10. 1, 2, 3, 4, 5 pair is also equal to 10. So check. We know how many the total yield is. And nothing was limiting because nothing is left over. And for something to be limiting, something else had to be left over because you used all of the limited one up, leaving excess of another. It's rare that in chemistry you just magically put the exact correct ratios together. So when we look at this one, we see that, again, you got to have 1 nitrogen for each 3 hydrogen pairs. And so they've circled those, leaving this as excess. So you're going to have a yield of 2, 4, 6. So 6 is the yield. And you have an excess of 2 nitrogen molecules after the reaction. So there they are, unreacted. 1, 2, 3, 4, 5, 6, indeed, is our yield. I know, it feels silly. I get it. But this is how some of the multiple choice questions are going to be even on your unit exam, because it is one of the components of the redesign to help you better conceptualize what's going on. It's, I guess, a way of saying we're not going to do math for the sake of math. We're going to do math as a way to help you understand what's happening. All right, so plan of attack. You've got to first realize you even need a plan of attack if you're going to do limiting reactant. And the way you know is that if you're ever faced with two starting amounts, the chances of you just randomly picking 2 starting amounts that are exactly matched for each other in a recipe are pretty slim. And that is the same scenario with the chemistry as well. So when you're faced with this situation, you calculate the moles of 2 things to get started. Okay, my computer has decided to stop. So my pen, there we go. We're back in business. All right, so when faced with this situation, calculate the number of moles of everything that you're given, and then you're going to have to step back and, dare I say, think. And you're going to have to ask yourself, what if all of one of this set of moles reacted? How many moles of the other would I need? Do I have enough? And if so, then I began with the limiting reactant. If not, then go at it again. Go back to the drawing board and go the other direction. Repeat the process with the other reactant amount you were given. It doesn't matter where you play this what-if game. It matters that you play it. So if that's clear as mud, then read on in these, and then I wrote you a note for class in case you hadn't been listening to me to listen to the screencast. There are some things in this course that the screencast may help you because we're all capable of learning. It comes down to the number of repetitions. There is no shame in listening to something over and over again. That's how you learn. You didn't learn your multiplication tables the first time they were presented to you. It may have taken you months to master those. Some people are still working on them years later. All right, so here's how we get started. So we're going to stick with this little Haber process with nitrogen reacting with hydrogen to make ammonia. It's a classic. It shows up in a lot of problems. So suppose that we have 25 kilograms of nitrogen reacting with 5 kilograms of hydrogen. So there's my two amounts. When in doubt, find the moles of both. So I'm going to scoot on down and indeed find the moles of both. So I take my 25,000 grams, because 25 kilograms is 25,000 grams, and divide it by the 28.02 that is the molar mass of nitrogen. I'm double checking my math as we go along through these notes, please. So 892 moles, no problem. And then 5,000 grams of hydrogen divided by its 2.02 molar mass, and I get 2,475 moles. But these are not comparable numbers because one of them goes with, in fact, I need 3 increments, and our increment is mole here, versus 1 increment. So you just pick one. So I'm going to pick what's sitting in my calculator because I'm lazy. What if 3 equals this, then what would 1 equal? Divide by 3. I would need 825. Examine. Do you have 825? Yes, you do. As a matter of fact, you have more than that. So I just found my limit. How do I know I found my limit? Because I need 825. So 892 minus 825, I know you could do it in your head, is 67. So 67 excess moles of N2, just in case someone asks. So I cross this out, and everything else I do from this point forward is going to be using 825 moles of nitrogen to figure out anything else that I need. Now, how many moles of ammonia can I make? Well, that's my 825 times 2. That's going to be 1650. I could do that in my head. 1650 moles of ammonia made, based on these two starting amounts. So let's go through it again. What if I use up all the moles of hydrogen? I would need 1/3 times, because of the 3:1 ratio here, I would need 1/3 of that 2,475. In my calculator, that's 825. Clearly, I have enough, so that's excess moles of nitrogen. So therefore, hydrogen is what limits me. I could have done it the other way around. It does not matter. You remember that phrase, 6 of one, half dozen of another? 6 is 6, whether I call it 6 or whether I call it half dozen. It doesn't matter where I start. The quantity is the same. So if I had started and said, okay, what if I use up all the moles of nitrogen? Then I would need 3 times the 892, and I would have needed 2,676, and clearly I do not have enough. I only have 2,475. So that limits me. So nitrogen is in excess. And I come back to the drawing board, start with the hydrogen, and go forward again. It's going to take you some practice to get good at this. Hopefully you practiced in first year chemistry, and you're going, I'm going to fast forward through this stuff because I already know how to do this. All right, so either way, I've established that either way I looked at it, whichever place I started, hydrogen's a limiting reactant. So keep that in your head. So I'm going to modify the table, and this is my crossing out, and so I'm not going to use this much. I'm going to use the 825, and the amount of that 825 means 23,116 grams were used. They had given me 25 to start with, and so 1,884 grams excess from subtraction. 25,000 minus the 23,116 that 825 moles yields at a molar mass of 28.02. 23,116 is 1884. Check. That's where that came from. Then, how much can I produce? Well, if 1 is 825, then you double it. I'm going to clear my screen. Stay with me. If 1 mole of hydrogen is, if 1 mole of nitrogen is 825, and I need twice as much of the ammonia. I just multiply by 2. That's how many moles of ammonia that are produced. And then if I multiply by this molar mass up here, that's why it's convenient to have it up there, 17.04, that's how many grams I made. So I made 28,116 grams of this. So this method lends itself to multi-step problems. You may find dimensional analysis faster on a single-step problem, but most of the AP problems are going to lead you through several calculations where stoichiometry is involved, and it's not always just simple, can you find the number of moles? All right, so what mass of the reactant was in excess? We just did that with 3 sig figs. All right, so here we go again. Exercise 18. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. Hey, they haven't given me a balanced equation. Perhaps I'm going to have to come up with that on my own. The other products of the reaction are solid copper and water vapor. Okay, at least it was kind for them to tell me that. If a sample containing 18.1 grams of ammonia, circle this stuff, underline this stuff. You don't want to reread this whole paragraph and try to find that value again. And it's reacted with 90.4 grams of CuO. Which is the limiting reactant, and how many grams of N2 will be formed? All right, how many sig figs do you see? 3 is correct. So I'm going to go ahead and just write myself a little note, get in the habit of doing it, 3 sig figs. What is my balanced equation? They told me it's ammonia. I know that to be NH3. And they told me that's going to react with CuO. They were kind enough to give me that formula. They gave me both these formulas, actually, ultimately. They wanted to tease me a little bit in the beginning. And then how many grams of nitrogen will form? I'm not making that. And then also copper, solid copper, and water vapor. So Cu and H2O. So let's get the molar mass of everything. And again, once you get skilled at this, you'll figure out what you do and don't need, and you won't waste time getting the molar mass of everything. So 14.01 for the ammonia plus 3.03. I can do that in my head. That's 17.04 for the ammonia. Got to look up copper. 55.45 comes to mind. Oh, 63.55. I would have been wrong. So 63.55 plus 16 for that oxygen gives me 79.55. Nitrogen, 14.02 twice. 14.01 twice, sorry. Copper, we just looked up, 63.55. I do have a little bit of short-term memory left at my age. And then water is lovingly 18.02. All right, so now what? Let's balance this sucker. Zero in on that right away. So I'm going to need 2 of those. And now I'm going to need 3 of these. 2-3 trick, as I call it. And what else is screwed up? That means I've got 3 O's, so I'm going to need 3 of those. So I'm going to have to fix that with 3 of these. Double check. A 2 to 3 to 1 to 3 to 3 mole to mole ratio. So this is my mole to mole. All right, so we need to find the moles of something, anything. Let's find the moles of both of these things because they gave us 2 starting amounts. So I've got the 18.1 grams of ammonia, and I've got the 90.4 grams of CuO, copper 2 oxide, that is. Clear this out, and I've got 18.1 divided by 17.04, and that comes out to be 1.06 moles. I'm doing a different color for you, I'm doing green. 1.06 moles. Therefore, well, I'll get to the therefore in a second. Let me make that prettier. Moles. Okay, let's do the same thing on the other side. 90.4 divided by its molar mass of 79.55, and I come out with 1.14. You cannot compare these exactly and go, oh look, 1.06 is less than 1.14. Can't do that because there's 2 and a 3, not a 2 and a 2 or a 3 and a 3. In other words, they're not a 1-to-1 ratio. So it's not that simple. So pick one and kind of think about it. I'm going to take this one because I have a feeling that I have, well, I know I could just do the math quickly in my head, that this is roughly zero point 0.5, so this needs to be roughly 1.5 since there's a 2 and a 3 there. But if you can't do that, just pick one. Just pick one and start. So I'm going to take this and divide it by 3. So I'm still got that number right here. This number is still sitting in my calculator. I'm going to divide it by 3. That's what 1 would be. But I need 2. I need twice that much. So I'm going to double it. So times 2. And I ask myself, do I have enough? And the answer is yes. I'm comparing that 0.757 to 1.06. Yeah, I got plenty. I'm not going to use 1.06. There's going to be some left over. But I am going to use 0.758 of it. So I know that 0.758 is what 1 or what 2 equals. I'm going to divide that by 2 and I'll get what 1 equals. So 0.37, let's call it 9 moles of this is going to be made. And then I also know I'm going to make 1.14 and 1.14 moles of these. How do I know that? How do you know that, you ask? Because we already figured that out. So I draw a line through the one I'm not going to use. So I could subtract right now 1.06 minus 0.758 and figure out the excess if they'd asked me that. And then I could even multiply it by the molar mass and get the excess in grams. So you can do all kinds of things with this once you can visually see what is actually happening here. So this is my limit. So I've got excess over here because of that 1.06 being larger than what I need of the 0.758. But what did they ask me? They asked me how many grams of N2 will form. So I'm looking at this 0.379 and I'm going to multiply it by its molar mass of the 28.02. So I've left it in my calculator. I'm just going to multiply it by 28.02 and I get 10.61. How many sig figs? 3. I see it right there. Good thing I already thought about that. So therefore 10.6 grams of N2 formed. Again, I say, now they can ask me all sorts of other things. They can ask me, well, how many grams of ammonia would be left over? I would take this number of moles and I'd multiply by 17.04. They can ask me, how many grams of copper would I make? Well, once you figure out this mole-to-mole ratio, you're just going to multiply moles by molar mass. Moles by molar mass for water. So it's really easy to do the multi-step problems this way. A lot easier and faster than dimensional analysis. But I am not trying to change you. If you are not broken, I am not trying to change you. I've had students that could do dimensional analysis faster than I can do this. I want you to be comfortable, I want you to be confident, and I want you to be fast. Alright, so we are nearing the finish line, folks, and thanks for your patience. This is our last concept, and it's one that you probably already encountered in first year chem. Theoretical, actual, and percent yield. Theoretical yield is the amount of product formed when a limiting reactant is completely consumed. In other words, everything went 100% perfectly correct. Yeah, not likely. You've been in a chem lab before, right? Nothing goes perfectly. I can't even make anything go perfectly in the kitchen. The actual yield is that which is realistic. That's what you really got. In other words, this is your result. You do the experiment and you own it. Whether that is a good result or a bad result, it's your result. You're married to it. You own it. Percent yield is to take the ratio of the two. Take your actual yield and take your theoretical yield, and obviously you're going to get a fraction. You multiply it by 100% to get a percent yield. Whatever that number comes out, you better slap that percent sign on it because we will dock you a point if you don't, because you're not asking the question that was asked. If they ask you for percent yield, 0.25 meaning 25% doesn't cut it, because there's a big difference between having, a quarter in your pocket and $25 in your pocket. So that decimal place does matter, and the percent part matters when you report your answers. So just be really careful about that. Don't get sloppy. All right, so here we go. Let's try it. I'll go with blue this time. All right, so methanol, kind enough to give me the formula of CH3OH, is also called methyl alcohol because the grown-ups in your life can't get along. It's the simplest alcohol of all because it only has one carbon. It's used as a fuel in race cars and a potential replacement for gasoline. So you may have seen methanol on gas pumps because it is now starting to actually be on the market. So methanol can be manufactured by the combination of gaseous carbon monoxide and hydrogen. Suppose 68.5 kilograms of CO, how kind of them to tell us what carbon monoxide was, is reacted with 8.60 kilograms of H2. I suspect you knew H2. You didn't need them to tell you that. And they told you that you're going to make methanol as a result. Now that may annoy you to write it CH3OH because you may not see that there are 4 hydrogens there when you start balancing. So there are 4 hydrogens there. Trust me. 1 C and 1 O. So you know what to do. We need to put a 2 right here. And now everything is balanced. So we have a 1 to 2 to 1 mole to mole ratio. And we might as well get our molar masses. 12.01 plus 16. I could have done this in my head. 28.01. 28. Oops, I wanted red. Didn't click the right thing. 28.01. Hydrogen is 2.02. And CH3, okay, I'm going to have to do that one. So 12.01 for that carbon, plus 4.04 for all of those hydrogens that are there, plus 16. 32.05. All right, then I need moles of somebody, anything. They gave me the 2 starting amounts. Little bell needs to start going off in your head. Hey, you gave me 2 starting amounts. Dang it, I'm in the land of limiting reactant. And they keep giving them to me in kilograms as well, just to see if I'm paying attention. So I have 68,500 grams of carbon monoxide, 8,600 grams of H2. Find the moles of both, step back and compare with this 1:2 ratio in mind. So this is my amount. Now I need number of moles. So 68,500 divided by 28.01, and I get 2,440, what do you want to call it? Let's call it 6 moles. So 8,600 divided by 2.02 is 42.57. Now I know what you're thinking. You're just looking at those raw numbers and you're thinking, hey, 2446 is a wimp. Well, you're not taking into account the mole-to-mole ratio. So that 42.57 goes with 2. So I have a habit of being lazy and just saying, if I divide that by 2, I'll see what 1 looks like. Divide it by 2, that's what 1 looks like. Do I have enough? Yes, I have plenty. I have 2446. I need 2128. I have just found what my limit is. So this is the limit. And I'm not going to use that because I really only need to use twice that, or half as much as the 4257, which was 2129. I'll just round it off. Moles. So that's how much I'm really going to use. So I've identified my limit. They haven't asked me to, but I'm going to have to actually calculate the theoretical yield of this sucker. All right, so how much did I produce then? So therefore, 2129 moles of this was produced. Therefore, what's sitting in my calculator exactly times that molar mass of 32.05 is how many grams? So 68,225 is close enough grams of methanol formed. Now that is theoretical. That's if everything went exactly right. Oops, I went too far. Apologies. Okay, so if everything went right, let me get the whole thing on the screen for you. That's the best I can do. All right, so theoretically, so how do I do percent yield? Percent yield is equal to the amount that we had that they gave us right there. I'm looking for that. And they've got it in scientific notation. So that's 35,000, and you can leave it in scientific notation if you're happier with that. I'm not, so I take it out. So 35,700, have to make sure I did that right, grams is what we really got. So that's my actual. And then what was my theoretical? My theoretical was 68,225. Why do I have 68,225? I think it's this. 68. Oh, that's why. Right there. 68,225. Theoretically formed, not the starting amount that I had. All right, so if I got that right, and then don't forget your times 100%. So you ready? 35,700 divided by that 68,225 that's sitting there equals, I like to do that first, times 100. And you come out with 52.3%. Love it when I get the correct answer. So 6.82 times 10 to the fourth. I think really that's a typo. It should be 6.8. No, it is 6.82. Did I write something wrong? No, I didn't. Okay, so yeah, here it is, right there. I circled it in pink even. So 6.82 would put it in 3 sig figs times 10 to the fourth, back in scientific notation, as grams. Mine was in grams to start with. So they just wrote it in scientific notation. I'm confusing myself now. Which means it's time to stop, right? That's what that means. So you may have to listen to this over and over again. You may have to listen to this only once. It all depends on how many repetitions you need. So it depends on the experiences that led you to this point. But trust me when I tell you, I am friend, not foe. We may get to know each other quite well, at least electronically. And you need to be good at stoichiometry. It is going to make a huge difference in your AP Chem score and all your test scores all year long in this course. So until next time, I hope you have a great rest of your day.